Hello everyone, it's my pleasure to share our recent work with you here, entitled UAV Mounted SIM, a hybrid option electronic neural network for DoA estimation. I'm Lin Shining, a master's student from the University of Electronic Science and Technology of China. Here's a brief outline of this presentation. Let me begin by explaining SIM in our title. SIM stands for Stock Intelligent Metasurface, which consists of multiple transmissive metasurface layers. Each layer contains a large number of meta-atoms that can control EM waves. As shown in figure, they act as secondary sources, generating secondary waves propagating to all meta-atoms in the next layer. The signal received at each meta-atom in the next layer is a weighted sum of the signals radiated by all meta-atoms in the previous layer, combined with the programmability of meta-atoms. This allows the SIM to function as a specialized computational device. Crucially, SIM's computation occurs during wave propagation. This means the processing time equals the wave's traversal time through the structure, which can achieve nanosecond scale latency. Additionally, when employing nearly passive designs, the power consumption can be very low. Moreover, this recursive computation parallels ANN. The inter-layer wave propagation mimics fully connected layers, while meta-atoms operate similarly to neurons. Due to SIM's similarity to ANN and its characteristics of low latency and low power consumption, there have been many attempts to study SIM as a type of analog neural network, such as image recognition and DoA estimation. By the way, in recent years, there have been efforts to deploy it in the MIMO transceivers, similar to the popular hybrid beamforming, using it as a cheaper analog precoder. However, since the interlayer propagation of EM waves in SIM is a linear process, it is a shallow neural network mathematically, so its inference ability as a neural network still has a gap compared to traditional ANN, making it difficult to achieve complex functions. Therefore, there have been attempts to integrate nonlinearity in various ways based on SIM to enhance its inference abilities. This type of SIM-based neural network structure that integrates nonlinearity is called an EN neural network. Among them, the structure that directly connects SIM to a digital neural network is often called a hybrid option electronic neural network, which is also the structure we use this time. It is simple and flexible because it does not require additional hardware. Let me now explain the HOENN architecture implemented in our work. First, regarding the system module, as shown in left figure, the SIM is configured on the UAV, positioned in front of the antenna array. The UAV performs DoA estimation using HOENN, with a crucial feature. It only requires measuring the amplitude of received signals. We module the DoA estimation problem as a multi-level classification task for EM field patterns captured by the array. The HOENN takes the array signals received at the first layer of the SIM as its input, and outputs the corresponding angular spectrum. These spectrums generate peaks at positions corresponding to DoAs, where DoA estimation is achieved through peak detection. Next, we will present the difference between our scene-based sensing receiver and conventional designs. The most significant distinction lies in our amplitude-only measurement approach. This eliminates stun conversion circles, whose cost and power consumption highly exceed those of amplitude measurement circles. Furthermore, amplitude measurements bypass phase synchronization challenges across array elements. Now let's discuss the mathematical modeling of sync EM wave propagation to the receiving array. Compared with traditional array signal modules, it is added a linear transformation determined by the scene's configuration. Specifically, when waves traverse a metasurface layer, they undergo linear modulation by meta-atoms, equivalent to multiplication by a diagonal matrix. Moreover, the assumed positive meta-atoms only apply phase modulation, neglecting energy loss during transmissions. Moreover, the interlayer propagation between metasurfaces essentially forces fully connected layers. The connection coefficients between meta-atoms across layers are modeled using release-morphic diffraction theory, which is primarily determined by the spacing between meta-atoms. In general, our framework features two components: tunable phase shifts and meta-atoms. They are optimized for DoA estimations, and fixed interlayer propagation matrices. They are determined by sin's geometric structure. Finally, let me present the complete forward propagation module of the HOENN used in our work. In summary, after passing through the scene, EM waves arrive at the receiving array. The array measures the amplitudes of received signals, which are then fed into a digital hidden layer to generate angular spectra. We employ a single fully connected layer as the digital hidden layer. Furthermore, we expand the scale of the network through time division multiplexing. Specifically, we divide the observation time into different time blocks. Within each block, the same phase shift configuration is varied, and the corresponding received signal amplitudes are recorded. After completing observations, these amplitude measurements from different time blocks are combined and input to the digital hidden layer. This time division multiplexing approach increases the number of neurons without altering the physical count of meta-atoms. In addition to angular spectrum generation with HOENN, we have developed a hierarchical DoA estimation method. We, we divide the entire DoA estimation into two parts: cost estimation and phi estimation. In the cost estimation stage, we first generate a low-resolution angular spectrum and narrow down the potential region range of DoA based on the positions of the spectral peaks. In the phi estimation stage, we then generate a high-resolution angular spectrum within the potential region determined by the cost estimation to determine the final DoA estimation result. Specifically, each resolution unit in the low-resolution spectrum corresponds to an HOENN. This HOENN can generate a high-resolution subspectrum within the range of the corresponding unit. By generating and stitching this subspectra, we can obtain the final high-resolution angular spectrum. The hierarchical DoA estimation method, by narrowing the detection range of HOENN, increases the final DoA estimation accuracy and reduces the computational complexity of the digital hidden layer. Next, I will briefly introduce the training procedure of HOENN. First is the forward propagation module, as shown in the left figure. Compared to the inference phase, a softmax layer is added, using cross entropy as the loss function and the add-in optimizer for optimization. The entire training process is conducted on the computer. And as mentioned earlier, during the phi estimation stage, HOENN only generates subspectra. The table on the right shows the labeling method we decide for multi-signal samples when training the HOENNs used for phi estimation. In summary, when there are DOAs within the detection range of HOENN in the sample, we ignore the DOAs outside the detection range and consider the probability of a signal existing within a certain resolution unit to be proportional to the number of sample DOAs within it. When there are no DOAs from the sample within the detection range, we assume that the probability of signals existing is equal across all units. This labeling method can reduce the interference of signals outside the detection range on the angular spectrum. So far, the algorithm part has been basically introduced, and next are the simulation results. First is the simulation setup, where some main simulation parameters are presented. Maybe some physical dimensions expressed in wavelengths. We assume that a UPA array is configured on the UAV for 2D DOA estimation. Then come the simulation results. First, this is the angular spectrum generated by using HOENN, including a global angular spectrum and a local angular spectrum, both with the same resolution, about 0.8 degree. We can see that both angular spectra generate spectral peaks at positions corresponding to the incident angle, which indicates that the trained HOENN has ability to generate effective angular spectra. And this figure compares the performance of different networks. The red line represents HOENN. The black line represents the same part in HOENN, and the blue line represents the digital part. Obviously, the performance of HOENN is better than other networks, which reflects the synergistic gain of combining the option and electronic components. In conclusion, let me briefly summarize our work. First, we design a DOA estimation method based on HOENN. The HOENN consists of SIM and a fully connected layer, and it only requires measuring the amplitude of the received signal. Compared to traditional methods, it has lower complexity and power consumption. Additionally, we design a hierarchical estimation method to enhance performance and reduce digital burden. Finally, simulation results validate the effectiveness of our algorithms. Here are some references related to our work. Feel free to look them up if you are interested. Thank you your attention.